Welcome welcome back everybody. I hope you had a great weekend and welcome to a new week. I wanted to first give you some of the standard messages which we have basically every week, and just to quickly remind you of where you find the information. So we do have this GitHub address where we place all the information, and let me just put that one into the chat here so everybody is on the same page. So let me just quickly bring that up here. And let me just take away some of these icons at the same time. So to quickly remind you of the GitHub address where you find all the teaching material. So let me just put that one into the chat so everybody can see that one. So this is the basic GitHub address. And if you scroll down, as we mentioned last week and the week before, you will find the handwritten notes and the videos of the lectures. They will be displayed at this README file. And you can see now that we are at October 10th, and there is obviously no lecture to display and no handwritten notes, but you can always revisit what we did after the lecture. And normally these videos are uploaded rather quickly after the lectures. So you should have access to them in, say, something like 2 to 3 hours afterwards. And the subtitles are normally generated during the next day. The thing I also want to remind you, if you don't want to be online and access the material, you can always clone down the whole repository by clicking on code here. You can decide whether you want to clone down with git clone, or whether you want to use a graphical user interface or just download the zip file. If you set up Git as a version control software and have everything installed, you can just do a Git pull and you will get the latest update always. Alternatively, if you're offline, you can always go to the doc folder if you have pulled down everything. And if you go to the pub folder here for the published material, you will then find typically material day 1, day 2, day 3, the introductory notes, which we had in the very beginning. So if you typically go into one of these day 2 here, you will find the HTML files which you can display on your own browser without being online, in case you are not online. That's can happen if you're out traveling and don't have access to a wireless network. That was quickly about the material. Feel free to come with questions if you have them. If there's something which is unclear about the teaching material, because I wanted now to remind you a little bit of where we were last time and bring up the topics which we are going to cover today. So let me just stop sharing here, and then we bring up a new share. And before we do that, I also wanted to say a little bit about the possible meeting which we can have in person. And one of the possible weekends is the weekend of November 5, 6, and then Monday 7th of November. So that means we could meet on Sunday the 6th of November. I'm going to put this in a chat, and I'm going to send an email to everybody. So whether we could meet on November the 6th, because that would also fit with the discussion of the first project and also some of the exercises. And then also have November the 7th, which is a Monday. So for November the 7th, we would have the lecture in person. And for those who want to hang around, we can always discuss further the project. But I was thinking of taking the afternoon of Sunday, the 6th of November. So this is one possibility. So I just put up the date in the chat here. And give it a thought and just send me feedback. I'm going to send an email to everybody about these possible dates for an in-person meeting. And that would actually fit well, because then we have covered enough material and we've started to discuss project number 1 as well. So feel free to ask questions. I mean, put them in the chat or just unmute yourself and ask questions. So what I wanted to bring up now, and if you look at the slides for last week, we started discussing ordinary linear regression. And the topic which we are going to enter now is ridge regression and lasso regression. But we are going to have to make some small detours before we start with that. And we are going to look at some technicalities with the scikit-learn about how to split the data and also how to scale the data. And there is an example in the slides, which I'm going to go through via the slides. And you will find that useful when you're actually looking at the first project and when you're thinking on how to scale the data. So ridge regression and lasso regression are methods which we are going to cover. And also next week, we are going to dive into resampling techniques and the so-called bias variance trade-off. And then we have actually enough material so that we can get started with the first project or parts of the first project. The reason why we do a linear regression as a kind of machine learning method was we dubbed it last week, as a kind of low-level machine learning method. We have the possibility to find analytical expressions for the estimators or the parameters or just the fitting parameters of the model which we made. The model is a linear model in the unknown parameters beta. We have analytical expression for statistical properties like mean values, the variances, confidence intervals, and more. We can make nice probabilistic interpretations, actually, and you will see that we can derive the same equations using a probability distribution for the variables y, which is our output, and then in terms of a normal distribution, we can then derive the same equation which we got by standard linear algebra. We can also, and this is something which becomes important later, we can also discuss so-called gradient methods, and in particular, this becomes very important when we are going to neural networks where we do not have nice analytical expression for the gradients. So remember that when we were trying to derive the parameters, the best parameters of the model, what we did was to take the derivative or the gradient of the cost function. And we required that these gradients are zero. And in that, with that recipe, we could then find the parameters beta. And for linear regression and ordinary least squares, these are given by analytical expressions where we simply have to invert a matrix. Now, the thing which I wanted to just move on a little bit with is some examples before we look a little bit more about the technicality of scaling the data, which is also an important feature. There's a question in the chat. Are those dates for in-person meeting? I was thinking of these dates as for in-person meeting, indeed. And because the doing things remotely like we are doing now is not satisfactory in the length, in the long run, because we need to discuss technicalities around the projects, and it's okay to meet and go through things more at a quieter pace and have this kind of one-to-one discussions, which often are simply just needed in order to understand properly what the projects are about. So project one is a project which we are going to release when we have gone through the linear regression mathematics and the different topics which we need. So that would be by after next week. And then when you have started to look at it, we can then meet in person. Yeah, I see there's a message here that we have a break during those dates. And so that means that some of you may be gone that period. So we just simply need to find a period which fits everybody here. Then I'm going to mail you about possible weekends, and you just send me a mail back whether this fits or not. Oh, good. Thanks for the input. So if we just go down, I'm not going to repeat all the things which we did last time, but one of the important things which we found with linear regression is that we have a nice expression for the parameters beta. And as we will see today, if we cannot invert this matrix, there are ways we can circumvent the inversion of the design matrix, the transpose times x, the inverse of that multiplied with transpose times the output vector. So y is the output. And for methods like ordinary least squares, we have something like a singular value decomposition, which we will discuss a little bit later. Now, one of the things which we looked at last time was to set up our own code for ordinary least squares. And in that specific case, one of the things we would do is actually simply to set up a matrix inversion. And you can decide whether you want to do the pseudo-inverse, which we're going to explain later today, or just the plain inverse. The pseudo-inverse uses the singular value decomposition, and we normally recommend using that one. So I'm going to emphasize that in the slides here. Recommended to use the pseudo-inverse. And that's based on the singular value decomposition. So this is an SVD based algorithm, and this is one of the topics which we will discuss today. Then, when we have done so, we can simply calculate the model, the output which we have, and then compare that with the data set which we have, and use this y tilde to compute the cost function and see whether we can drive the cost function to 0. Ideally, we want that one to be 0. So that's one way to assess the quality of the data. And as we mentioned last time, if you use numerical Python, it has actually a least squares included. This uses, however, standard matrix inversion algorithm. So in case the matrix has singularities near singular, we would end up with problems. Now, another thing which we ended up discussing was a calculation of the mean square error, relative errors, and so on. And we looked at this at the data for the binding energy for nuclei. And this is a useful data for us who are doing nuclear physics. Now, there are some other technicalities here, like the chi-square function, which I will not cover. So the chi-squared requires that you actually, instead of looking at the standard cost function, you do actually have an expression for the variance of the system. And that means that you would need to plug that in. What we have done is simply to put that quantity equal to 1. So the expressions here are expressions which we're not going to repeat, but I wanted to what I wanted to say a little bit about when we move down here. There are several examples which you can look at, and one of these is now going to include this ridge regression, which we will discuss pretty soon here. So this is a data set which takes in an equation of state for nuclear matter and as a function of density. So this is the energy per particle as a function of density. And this file which we read in here, which you have access to, this EOS, this is a comma separated value file where the first column contains the density and the second column contains the energy per particle. And then using pandas, we read in the data here and we make a column which we call density and another column which we call energy. As you can see here, we're setting up the arrays which contain energies and densities. And then we are making a fit now where we also include the intercept. And this is something now which we are going to discuss a little bit more in detail, how we can include or exclude the intercept and why we should do that, and maybe why we should not do that. And this becomes also important when we want to compare our own code with scikit-learn. So this is the design matrix which we would set up in this specific case. We have a polynomial as a function of density. We keep an intercept. We have the density to the power of 2/3, the density to the power of 1, and the density to the power of 4 divided by 3. And here I've simply used the scikit-learn optionality. Keep now in mind that this is linear regression in the parameter beta. In here, on the other hand, when I'm setting up the design matrix, I can have a polynomial of different degrees. So just remember that when we say linear regression now, it's a linear equation in terms of the unknown parameters beta. And here we calculate the y tilde, we print out the different coefficients and then also the intercept. And now we're also going to run a calculation with this ridge regression. And this is pretty simple. The only difference between this one and ordinary least squares is that we need a so-called hyperparameter lambda, which we can typically tune in order to reduce the mean squared error. So the type of functionality which we're dealing with is very much the same. So we now have ridge instead of ordinary least squares. And then when we've gotten that one, we can perform our fitting as before, and we can make the prediction as before. And this specific case, we're actually running these calculations for the mean squared error. And in this particular case, when I do ordinary least squares, you see now that the mean squared error is not, is not impressive. And we also have a mean squared error when we do ridge regression with the lambda equals 0.1, which is also not very good, which is 197. So it means that here there is actually something we need to think of. So one thing which is pretty common to do with a data set, and we discussed that partly last week, is to split the data into train and test. Now, scikit-learn has this nice functionality that it actually provides us with a function which splits the data in train and test. And here I have added the R2 score, the mean squared error. It's the same data set. I'm reading the file again. I'm setting up the same design matrix as before, except that here I've now augmented my polynomial complexity to a polynomial which goes like density to the power of 5 divided by 3. So what I've done, for those of you who are more familiar with this kind of equation of state fitting, is that I've added something which goes as a function of the density to the power of 5/3, and this is going to mimic relativistic corrections. So in the previous case, we actually stopped at 4 divided by 3. Furthermore, what I'm doing now is I'm splitting my training data and test data into a test part and a training part. And there is no kind of magic number for how much you should put in test and how much you should put in training. But normally you try to put as much data as possible to train the model, and then you leave a certain amount of data which has not been trained, used to train. And this is the data which you can think of as untouched data, and then you will test your model on that data set. This is going to become more and more important because we actually want to avoid the problem of overfitting. And overfitting is a serious problem in all these calculations because we can tune a model which fits perfectly the data we have. We can make it so nice and so well fit to the data that we fail miserably when we are going to apply our model to data which was not included in the training set. So it's pretty common to take out some data, put that in a vault, and just leave it there. And then when you've trained a model, you come back and then you apply it to the model. And in this specific case, we are just doing a standard linear algebra inversion. Here we can calculate the pseudo-inverse if we want to. And I am making a prediction with my test design data, and I multiply that with beta. So here I produce my training data, and this is my training output, y tilde. And here I'm putting my test output. This is my prediction. That's why I call it y predict here. This means that if you look at the numbers now, also because I included the higher order degree of the polynomial, you see now that the training mean squared error has actually dropped quite a lot. And sometimes you may actually find that the test mean squared error can be lower than the training mean squared error. That happens. But this is a typical case where we, one, have increased the complexity of the model. We presumably have made a better model because we moved down from a error which was on the order of 12 or something. If we look back here, we had now an error which was 12.36, and by adding a higher degree polynomial, we end up with an error now which is smaller. It's actually 7.14. This is the R2 score, which ideally should be close to 1, but we see now that from the MS mean squared error, we are not that happy with the results. Now, if you now scroll down, there are more examples here. I'm not going to go through all of this now. I invite you to play around a little bit. But what I wanted to discuss a little bit with now is with you now is the calculation of the intercept or not, and including that in the fit, and scaling our data. So if we go into the slides for what we call day 2 or session 2 here, we are going now to discuss both ridge and lasso regression, but I wanted to bring up this example which you see here now. So there's a very important part of the data analysis, and that deals with the pre-processing of our data. So sometimes you may have data which span many orders of magnitude, and then it can be convenient to scale this data to a domain of, let's say, 0 to 10, as an example. It's always important to look at your data, because sometimes your data may be punched in wrongly. So we've had cases where data over wind velocity, wind speed, were punched in one time period as meters per second, whereas for another time period, they were punched in as kilometer per hour. And clearly, if you don't notice this immediately, this can actually lead to pretty, poor outcomes for the fitting of your model. So if you have a data set could detail health habits, they may have features such as age, which would typically be in the range from 0 to 80. There could be calorie intake of over 2000. And many machine learning methods are actually sensitive to the scales of the features and may perform poorly if they have very, very different scales. And that's why scaling is an important thing to think about. So in the first project you're going to see, we're going to have a kind of vanilla case where the data for X and Y, so this is a three-dimensional function, where the data in the X and Y direction are already scaled for you because they are produced for an interval between 0 and 1. So we could easily say that these are scale data. But scikit-learn has quite some functionality. And it's important to be aware of these types of functionalities because they do things for us which can lead us to perhaps misinterpret the results. Now, in particular, this applies to you comparing your codes with scikit-learn. So scikit-learn, by default, does actually do some scaling for you. And sometimes this can lead to frustrations because you cannot reproduce the data from scikit-learn with your code. So let me step you through these elements here. So the standard scaler, what that one is doing is that it takes your design matrix and it subtracts the mean from each column. So let's quickly set up that one and go back to the whiteboard. So the standard scaler, let me just set up the date here. And let's quickly switch to the whiteboard. So scikit-learn has a lot of functionality here. And this functionality is something which we need to think a little bit about. So there's something which is called the standard scaler. So if we look at what that one is doing, so the standard scaler, in many cases it can be convenient to actually write a code which does it, instead of relying upon functionalities where you may be a little bit uncertain of what this functionality is actually doing. So if you now think of the design matrix, so you would have a set of columns. So you would have a column with an x00, x01. So this is our first column. And this goes all the way, x, this is the opposite, sorry for that, x10. And this goes down to xn minus 10. You have an x01, x02, and this goes all the way up to x0p minus 1. And here we have the element xn minus 1 of p minus 1. Now we can rewrite this in a more compact form as different vectors. So we would have a matrix now which has a vector, let's call this vector x0, and then we have the vector x1, etc., up to the vector xp minus 1. So we have p columns. That means we have vectors from x0 to xp minus 1. So each one of these contains then the elements which you see in here. So all these elements here define the vector x0. Now what we can define now is a quantity which we call mu0, which is now simply 1 over n. And then we sum over I equals 0 to n minus 1. And then we take x of I, and then we have 0 here. So that calculates the mean. And that means that we are going to get a new design matrix. So x goes over to an x bar. And this x bar now is actually given by these vectors x0 minus mu0. And what I'm going to put now is a new label x0. And then we are going to have x1, x2, up to xp minus 1. So each of the vectors with a bar on top of it, these are vectors where we have subtracted the mean value for that specific column. Now, one of the reasons why we do this is that we would like to perhaps, hopefully, we want to reduce the role of outliers. So we find a mean value for all the data set. This can lead to a better fitting. Let's go back to the Jupyter notebook now and continue a little bit along this discussion of the standard scalar. So the standard scalar also, if you provide the variance, it would divide by the variance as well. But by default, it puts the variance equal to 1 if you don't provide a variance. So this scaling is the one which is normally always used, and scikit-learn, unless you specify it, it does this by default for you. Then we have something like the min-max scalar, which can be very useful. And this is a scalar which scales your data for all the features to lie between 0 and 1. This can be useful if you have data sets which vary wildly. Normally, you need to play around a little bit with these types of scaling functionalities. We also have something which is called normalizer that scales each data point such that the feature vector has a Euclidean length of 1. That's another way of doing it. We have something which is called a robust scalar. I invite you just to look it up and read about it. But the two ones which are most used are actually the standard scalar and the min-max scalar. Now, this becomes important now if we want to compare our own code with scikit-learn. So mathematically, the standard scalar is doing what you see here. It takes the matrix elements, subtracts the mean value, and divides by the standard deviation. And normally the standard deviation is set to 1. So let's take a closer look at this type of scaling. So what is this doing for us? So the standard scalar, as we said now, is a function which is baked in scikit-learn. But before you start using the machine learning algorithms, you should always take a look at the data with a critical assessment of them in case you need to scale them. So you have to make this judgment. Do I need to scale my data? So if you can go through the data, if you can do that, if that's feasible, then you should always try to do that and see if you can gain some insight by just looking at the data or plotting the data. Sometimes, if you need to scale the data, not doing so will give an unfair penalization of the parameters since their magnitude depends on the scale of their corresponding predictor. So, as again, you have the example here. If you have an input given by the heights of different persons, human height may be measured in inches or meters or kilometer. If measured in kilometers, then the linear regression model with this predictor will probably give a much bigger coefficient term than if measured in millimeter. And this can clearly lead to problems in evaluating the cost or loss function. So there are such things to think of, whether it's convenient to run the calculations in kilometer or meters, or like we did last week when we looked at the binding energy per nucleon when then we had the energy which came in kilo electron volt, and we scaled that one to mega electron volt. So let's take a closer look now at what is going to happen. And I invite you to take a look at the code which comes here. Now, this is a code where we run our calculations with and without a standard scaler. So the first equation here is just a simple case where we now have set up a function which has an intercept of 2, a slope of 0.5, and 3.7 as an x parameter. So we are looking at the second order polynomial. And I'm setting up a second order polynomial. And here I'm setting up the design matrix, and I'm including the intercept in the design matrix. And then I simply perform a fit, and then I include a scikit-learn because I want to compare my code with scikit-learn. And scikit-learn, if you want to do that, if you want to include the intercept, you have actually to do the opposite of what you think is natural. You have to put the intercept, fit intercept equal to false, as written here. And this is something which always confuses people. It actually confused me because I thought that I should put fit intercept true, that it then would actually perform the fit of the intercept, include the intercept in the fit. So the discussions which I'm presenting here, they apply to a polynomial fitting only, because that's where we have the intercept. So keep that in mind. This is a debate, a discussion which pertains mostly to fitting of functions which are parameterized in terms of a polynomial. So in the case here, I now perform my own fit. I have a function fit beta which actually inverts a matrix. So you can see that here. That just simply inverts the matrix. And then I compare it with scikit-learn. And I want to compare the two. Then I have another one where I now myself explicitly take away the intercept column, which contains only one. Because the intercept column, when I take out the mean squared value, because I'm scaling the matrix elements by subtracting the mean value of every column, clearly then the mean value of all the ones is equal to 1. So that means that I would just get a column there which has zeros. And if I want to invert that one, that would lead to problems. So what I need then is simply to take away that column. And now I set up a design matrix without the intercept. And then I use fit intercept true here. You actually don't need to do that, but I have emphasized it here. And then, as you will see a little bit below here, we have to be a little bit careful because we can now actually calculate the mean value. And this is what I do here with a fit now, which is done without the, where I subtracted the averages in each column here. So you can see now that the y offset is the average of the y values. X offset is now the average of all the columns. And I subtract that when I make the fit. You can see that x minus x offset and y minus y offset. And then I can recalculate when I parameterize the model with beta. Then I can extract the mean value from that one. Now, in this particular case, when we are doing ordinary least squares, there's not going to be any difference between the parameters and the mean squared error, which I get when I fit it like this. This becomes important when we are looking at the lasso and ridge regression. Now, if I run this now, you will see that my true beta, this is the value. I have a fitted beta here, which is done by my standard linear inversion. This is what scikit-learn gives. In this case, we keep the intercept. And you see now that the two methods, the one which I wrote and the one which is written by thousands of people involved with scikit-learn, they give the same result. And the mean squared error is obviously the same. Now, the next thing I can do now is actually to fit without the intercept. And in that case, you see now that I get the same result as I had before. And you see that here, beta 1 and beta 2 here. And the same when I use scikit-learn without the intercept, I get exactly the same. And what you see also in this specific case is that the mean squared error isn't changed. This can change when we move to Lasso and ridge regression, and you will see why. So in this case, we have results which are compatible with scikit-learn. Now, what happens here is actually that we have in the mathematics here, what is going to happen. So let me just bring back a little bit some of the, wait, I think I have put this, just a small moment. I need to remind myself where I actually put that derivation here. And it can happen. I actually put up a derivation which I was going to show, and now suddenly I don't remember where I put it. Let me try to find it. I just need to find that one. Sorry for this. I mean, I had the, if not, I will bring it up after the break here. So there's no crisis here. I must have copied it out. So let me just bring this up after the break here, because there is some simple mathematics which we can set up, which explains why I have these subtractions which you see here. So if you look at the scikit-learn result with and without the intercept, what I've done now is that when I want to calculate the intercept, when I'm doing a polynomial fit, there is a simple expression here where I take the mean value, the y values, minus this x, the design matrix, with the mean value subtracted, multiply with the parameter beta. So, and after the break, I'm just going to bring up the mathematics here. But what becomes important is actually that when we now introduce what's called ridge and lasso regression, normally what we do then is that we have a regularization parameter where we now take and penalize the fitting of the parameters beta with a parameter lambda. And if we now take away the intercept, this is going to give us a mean squared error, which potentially is smaller than the one which we have if we were to include the intercept. Now, the thing which I wanted to bring up now before we actually move on is the two methods which we called for lasso and ridge here. So let me switch back to the whiteboard, and then after the break, I'm going to bring up the equations which I was missing here in the slides. So let's bring that up after the break. But before we take a small break, I now wanted to remind you of what we've been doing in ordinary least squares. So let's just put this up here, OLS for ordinary least squares. So the assumption, the underlying assumption, and you can think of that as a model as well, is that our data is now described by a continuous deterministic function f of x plus some normally distributed noise. And this epsilon is now proportional with a normal distribution with zero mean and standard deviation and variance equal to 1. So what we found then is that beta, the optimal one for ordinary least squares, is equal to this design matrix, xt of x inverse x transpose times y. Now, if you look at the expressions which you have here, we know that in case the matrix cannot be inverted, we have to be a little bit careful. Now, the way this hyperparameter was introduced was not as a hyperparameter, but it was introduced as a simple way to cheat and avoid the problem with a matrix which could not be inverted. And the simplest way, if this matrix H, as we are going to call it later, of X transpose times X is not invertible, there is a simple trick which we can actually do in order to be able to invert a matrix. Has any one of you actually encountered that kind of trick? It's a very simple and cheap trick which we can apply to the matrix by adding something to the matrix elements. And by adding something which could be a small parameter lambda, then the matrix can actually be inverted. And you will be surprised to see that many codes which were written in the 60s and 70s in the previous century, even in the 80s, they could have a parameter which is called 0, which could be 10 to the minus 8 or 10 to the minus 10. And that was added to your data in order to avoid either division by zeros or matrices which could not be inverted. So if you think of this matrix S, H, what could you actually do in order to make this matrix invertible if it was not invertible? Let me see, there's a suggestion, there's some suggestions in the chat here. So you would simply add a constant. And if you add a constant, where would you add the constant? To which type of matrix elements? Any good suggestions? So let me see here, there's a new suggestion in the chat here. You could do it to all values, but perhaps you could do it only to some values. And that's actually the kind of recipe you end up with. And which values would you add it to make life simple here and actually to avoid, if you think of calculating the determinant?
My idea will be similar to calculate the eigenvalues, like lambda in the diagonals, and starts playing with the lambda parameter in order to not have a zero determinant, which will be translated as an invertible matrix.
Perfect. This is exactly the answer. So the cheapest and simplest trick you can do to make a matrix which you fear is not invertible. So what you could do now is to take this matrix and you will transform it to X transpose times X plus the diagonal matrix multiplied with a parameter lambda. Now, remember now that X has dimensionality of n times p. So that means that X transpose times X has dimensionality p times p. So it means that this matrix I is a matrix which we are going to write as an I of p here, just to indicate that this is a matrix of dimensionality p times p with only diagonal elements. Now, if you do that, and this is the kind of trick which people used previously, and people still use, in order to avoid either divisions by zero or matrices which cannot be inverted. But this actually leads us to what's normally called ridge regression. And you can actually get the same matrix by doing the following. So let's set this up. So we do ridge regression. And now we define a cost function as a function of beta, which is equal to 1 over n as before. So we have the standard cost function for linear regression. And then we have our y of I minus y of I tilde squared. But now we have an additional term, a lambda, which now contains a sum over j equals 0 up to p minus 1 of beta j squared. And we would typically write this, if you now are familiar with this norm 2 or vector. So if I write this one as a norm 2, this is actually given by the sum over I equals 0 to ni and to n. And then I have an x of I squared, but then we take the square root of this quantity. So the norm 2 is something we can now rewrite, use to rewrite what we have. And we introduced that a little bit earlier as well. So we would write this one as y, as vector form, as a norm 2 squared. So the 2 which you see here is actually stands for being squared. And then I would rewrite this as a lambda multiplied with beta norm 2 or L2 norm and squared. So this is normally called ridge regression. And if I now take the derivative with respect to beta, so if I take the same derivative which I did previously when I derived ordinary least squares, what we are going to get then is the following expression. So I'm going to get a minus 2 divided by n. I'm going to have my x transpose, and I'm going to have x minus y here. But then I'm going to have plus 2 times lambda multiplied with beta. And now beta is a vector here. Now this means now that I have to be a little bit careful when I'm setting up the expression. So this should also be, sorry, I am missing an expression here. So this should be an x times beta should be here, sorry. When I then put everything together and I single out the beta values, what I'm going to get then, and I multiply away the factor of n, that just redefines an lambda, which we can call lambda tilde or just plain lambda. What we get then is that beta of ridge, the optimal parameters, is going to be equal to x transpose times x plus lambda multiplied with the identity matrix inverse. And this is again multiplied with x transpose times y. And that's exactly the same expression, almost the same expression we had before, except that now we have this term added to the diagonal. So if I start with a problem to be optimized of this form, and I take the derivatives, as we did with ordinary least squares, it's the same way to calculate them, then I end up with an expression now which will never produce a determinant or an inverse which is singular, and that means as long as we have lambda different from 0. So with lambda different from 0 and larger than 0, this will always lead to the type of problems which we can invert without any problems. We always have to be a little bit careful when, in case values differ a lot, there can be numerical inaccuracies which get accumulated so that we accumulate errors which lead to loss of numerical precision. That is possible. But still, this is something which we can invert, and it saves the day for us. And the way we can think of it, and that is not in terms of a simple trick as we discussed here, but rather in terms of optimizing a new function, which is called the ridge function, then we can actually get the same expression which leads to a matrix which can be inverted. Now, the term lambda has a name in the literature, and it's called a hyperparameter or regularization parameter. And what we can show is that the mean squared error we get with a ridge regression can be smaller than the mean squared error than we get for ordinary least squares. So the hyperparameter or regularization parameter. And the term which we see here, this term lambda multiplied with the term beta, the L2 norm squared, is normally called a regularization term. So this is a hyperparameter or regularization parameter. And this is called a regularization or regularizer. Regularizer. Like that. So before we take a small break, let me add another way. So there's nothing magic with this term. So you can have something which is called lasso regression. And I'm coming back to what lasso stands for. In that particular case, what we have is that the term lambda of beta norm 2 squared goes simply over to lambda of the L1 norm. And that is given by lambda, and I have a sum over j equals 0 up to p minus 1. and this has simply the absolute value of beta j. Now, one thing you will see as problematic now is that, and it's quite easy to understand it, is that we are not going to get a nice analytical expression. So that means that we will need to solve these equations with a constraint. And we know that because if I take d of x of dx, we know that that one is given by 1 if x is larger than 0. Sorry, not equal to, because we have a discontinuity at 0. And then we have -1 when x is less than 0. Now, what most practitioners do actually is to set the derivative equal to 0 at x equal to 0, although there is a discontinuity. But these functions here, yeah, this is fully correct. There is never an optimal hyperparameter to choose, unfortunately. So this is a very good question. There's a question in the chat here, which I'm going to repeat here. But then we will have an extra choice of the hyperparameter that might get slightly different fitting, depending on my chosen value. Is an optimal hyperparameter to choose? We cannot a priori say which is the optimal parameter. We actually need to run a calculation over different hyperparameters, and then we would pick the hyperparameter and model which gives the smallest mean squared error, unfortunately. So you cannot a priori say which parameter is the best one. But what this does is actually penalizes specific values of beta in a specific way. And we're going to see that after the break, when we are going to discuss partly the singular value decomposition algorithm and the meaning of lasso and ridge regression. So I'm going to stop the recording now, or pause the recording. So before the break, I told you that I seemingly had taken out some text which should have been there in the slides. So I'm going to bring that back again. But now I just wanted to bring it up for you. And if you go into the chat, you will find the link to another set of slides where I have it. So it's seemingly I've actually taken it out without being aware of it. So centering, what that means mathematically, is something which sometimes puzzles us, and it's important when we are doing a polynomial fit. So if you think of a polynomial fit, what we have is a function of the type which you see here. So this is our cost function, and we are making a polynomial fit. So we have the parameters from the design matrix. We have beta 0, which is the intercept, and beta j. Now what you can do now, when you take the derivative of the cost function with respect to beta 0, you get a simple equation here. So you can see now that since you want this to be 0 for all the beta j's, beta 0 can then be isolated because it does not depend on the x's. And then we get an expression which contains the value, the sum over all the output values, minus the sum over the matrix elements multiplied with the unknown parameters beta j. You can manipulate this further. If you now sum up, because beta 0 is just a constant, you get n times beta 0. You divide it, and what you have then is that this is the mean value of y, which is something we can always calculate. So keep in mind that this is an argument which applies to a polynomial model. So when you have a polynomial model, you can choose to fit with or without the intercept. Now, when you add ridge regression and lasso regression, then you can actually penalize less or more if you fit with the intercept. And what you will typically see then is that the mean squared error, when you take out the intercept in ridge and lasso regression, tends to give a mean squared error which is smaller. Now what you see now is that you can rewrite these parameters. So now what I made now is an assumption that we only have beta 0 and beta 1. And that means that I can now put beta 1 out here. And then I have the mean value, which you see here, simply mean value of all the column elements, which I have. this is this y1, and you will get similar ones for all the other parameters. So that means that in the summation which you have, if you were now to, in this sum here, were to keep beta j's, you can take beta 1, beta 2, beta 3, and so on outside, and then you would get a sum, which is simply the mean value for a specific column multiplied with the parameter. And that means that this mu1 here, which we have defined, is actually this specific sum, and this mu of y is the sum over the y values, the mean values. So I can actually calculate when I found this parameter beta 1 from the fitting, then I can calculate beta 0 again using the mean value of the output and the mean values for each column multiplied with the parameter beta. So the general expression then is simply the expression which you see here. And this is something which you can then add to your results when you want the intercept and if you made the fit without the intercept. This, again, if you're dealing with a polynomial fit, if you have another type of functions you're using in your model, like a sine or cosine, etc., then clearly there won't be a number 1 in the first column. So this is just to keep in mind what this actually means when you do this type of scaling. In case of a polynomial approximation, because if you do a polynomial approximation and you use scikit-learn to compare with your own algorithms, it may happen that you don't get the same parameters. And that is because you have included the intercept, while scikit-learn does not include the intercept by default. So you would expect that if you put fit intercept equal to true, it would fit with the intercept, but it's actually the opposite. So this was a small digression on this fitting procedure. So what I wanted to do now is to go back to this Ridge-Lasso regression and look at how we can interpret that mathematically, because that has some important consequences for us in our basic understanding of what these algorithms are doing. So let's go back to the Jupyter Notebook for day 2 here. So let me now bring back the sharing. So in day 2, actually day 1 from last week, and also day 2, you will find the same slides. We have a discussion of the singular value decomposition, and this becomes very important for us. So the examples we have had when we've been looking at matrix inversions, they have often been of the type where we have a polynomial fit, and often then we don't have a problem with the inversion of the matrix. Mainly because each column then represents a polynomial order, and normally these will be quantities which are either orthogonal or close to being orthogonal. Now, however, if we have this, there's a way to circumvent it and calculate what's normally called the pseudo-inverse, and this is done by the singular value decomposition. Now, we are going to use the singular value decomposition to give an interpretation of what Ridge is doing compared with ordinary least squares, and we're also going to look at some examples with lasso and how we can interpret what is going on with lasso regression compared with Ridge regression versus ordinary least squares. Now, keep in mind also that you can show that when you use Ridge regression and lasso regression, in particular Ridge regression, you can actually show mathematically that you can get a mean squared error which is smaller as a function of this hyperparameter lambda. So if we look at the singular value decomposition, if you now look at a matrix like this is a matrix where the columns are linearly dependent. And that could be an example of a typical data set which you could encounter, that you have strong dependencies or near strong dependencies. So in this case, the first column is a row-wise sum of the other two columns. And the rank, in this case, of the column rank of a matrix is a dimension of the space spanned by the column vectors. This means that the rank of X is equal to the number of linearly independent columns. In this case, it actually has rank 2, whereas we would like to have it to have rank 3 if we want to calculate an inverse which is 0. So we often have matrices, even a square matrix does not need to have an inverse, and then we say that the matrix is singular. And if you look at this simple case here, this is a simple case where you see that the determinant is 0. And you see that immediately by just calculating it. So X is singular, and it means also that it has at least an eigenvalue which is 0. Now, this leads to what we discussed before the break, that one simple cheat which we can do to fix the singularity is simply to add, in a very ad hoc way, a small component to the diagonals of the matrix which we want to invert. And this actually is what the ridge regression gives us, but the way we can derive it is from a more fundamental point of view. So the parameter lambda, as we said, is actually called a hyperparameter. Now, what I wanted to say a little bit now is about the singular value decomposition theorem. I don't know how much you remember of the singular value, but just to remind you quickly of some basic linear algebra. So if you have a square matrix, it can only be diagonalized if it is what we call a normal matrix. And that means that if this X is an R times N matrix, then X transpose has to be equal to X transpose times X. Alternatively, it has to be the Hermitian conjugate. The matrix has a set of eigenpairs, and the eigenvalues are given by the diagonal matrix. But the matrix, if we now look at this matrix here, this matrix X, even if we cannot invert it, or if it had eigenvalues which are 0, we can always perform a singular value decomposition of the same matrix. In that case, these eigenvalues are no longer called eigenvectors, but they're called the singular values. So if we have a matrix which is obviously diagonalizable, then we know that there is a unitary transformation, which when we multiply the matrix U with the matrix U transpose, it gives the identity matrix. But as we saw, with that specific matrix which we had up here, that very simple example, which has a determinant equal to 0, this is the same matrix which you see here. This matrix cannot be diagonalized. Now then, even if that is the case, what the singular value decomposition says is that any matrix can be decomposed in terms of two orthogonal matrices and a matrix which now contains only the singular values, but some of the singular values can have value equal to 0. So that specific matrix which we have here, this matrix with 1s and -1 and -1, that can actually be rewritten in terms of a matrix U. Since this is a square matrix of dimensionality n times n, the dimensionalities are the same. But this will be the singular value decomposition of the matrix X. And these values, sigma 1 and sigma 2, are no longer called the eigenvalues, as we put it here, but they are called the singular values. So a singular value decomposition exists always. And this is a very powerful theorem. But what we are stating is that we can rewrite the matrix in terms of a matrix U, which is orthogonal, a matrix which contains the singular values, and an orthogonal matrix V. And if we now look at some examples here, we can always recode this matrix in terms of a singular value matrix and a matrix which is orthogonal U, and another matrix which is orthogonal V. In this specific case, the singular value decomposition gives eigenvalues or singular values, which is normally the word which is used, for sigma I is larger than equal than sigma I plus 1 for all I, and for dimension larger than I equal 2, which you see here, then these singular values are all 0. In the general case, where this matrix has a dimensionality n times p, the matrix can then be decomposed into an n times n orthogonal matrix U, a p times p orthogonal matrix V, and a diagonal matrix sigma with R, which is the minimum of n and p, and giving singular values sigma I, which are larger than 0. So the columns of U are normally called the left singular vectors, while the columns of V are called the right singular vectors. So let me just go through some of the simple examples which you can see here. So this is a simple matrix where we now have defined this matrix which gives the singular values, the matrix in the example above here. So this is a matrix which now actually gives problems. So what I'm going to do now is simply to perform the singular value decomposition of the matrix. So I use the singular value option in the linear algebra package of numerical Python. I set up now the transpose, as you can see here. I calculate the transpose of V. So this is what it returns. So the algorithm here returns U, the matrix with the singular values, the V transpose. And then I can clearly, what I can do now is simply to test by a brute force inversion and see whether my singular value decomposition is giving something which mimics what my brute force inversion actually is doing here. So running this one gives us first a test. So what you can see now when I calculate the transpose here, and so if I calculate the matrix V and I multiply that one with the inverse of D times U of T here, I should actually get back a matrix. And you can see now that what it does here is that my linear algebra gives problems because it has an inversion which it cannot be done. So if I go back now and comment it out, so let's just comment this out here. Okay, so let me just, I forgot to do that one. If I do this now, I can now calculate this matrix inverse, but you can see now that the inverse is not going to be equal to the pseudo-inverse. So this is a large number, which clearly reflects that there is a singularity. Now, what I've also calculated here is the matrix A, which is the transpose of X times X, as you can see here. And that clearly gives me now a matrix where I take the difference. So let me see now. It just returns. If you now look at these tests here, it returns the matrix U, it writes S and V of T here, but it also takes a transpose, and then it returns here these matrices, and then when it prints X here, it takes now and prints the matrix X, but then it takes also the transpose of X times X. And in this specific case, you can see that these quantities are equal to 0 along, it has a 0 here, and then it has a given set of matrix elements. But the main problem here is that the matrix has actually columns that are linear dependent, and the first column is the row-wise sum of the other two columns. And this matrix here needs actually to be inverted in order to calculate inverse with the so-called pseudo-inverse. And we are coming back to that a little bit later. So if you just perform the inverse of the matrix here, when you now have calculated the pseudo-inverse, no, not the pseudo-inverse, but we have actually calculated the transpose of X times X, and we try to use the singular value decomposition and try to invert this matrix directly, we are not going to get a reasonable result. And we are coming back to that when we calculate the pseudo-inverse. But before we do that, I wanted to look at some of the mathematical properties which we have with ridge and ordinary least squares, and why ridge is doing what it is doing and what it means. So let me go back to the whiteboard, and let's take a closer look at the singular value decomposition of ridge and ordinary least squares in order to get a feeling of what actually ridge regression is doing compared with ordinary least squares. So let me bring up the whiteboard here. So what we have said now is that we have defined a beta parameter for ordinary least squares, which is now given by the matrix to be inverted. And this is the equation which causes problems for us, multiplied with y. And then we have a beta optimal for ridge regression, which is equal to x transpose times x plus lambda multiplied with the identity matrix inverse multiplied with xt times y here. Now, what we are going to do now is to look at the matrix x transpose times x in terms of the singular value decomposition. So to quickly remind you, this is a matrix of dimensionality p times p. X is a matrix of dimensionality n times p. So we're going to do several things here, because many of these concepts which you're looking at, they link also with a statistical interpretation, which will come handy a little bit later. But what we assume now is that this x has a singular value decomposition. So it's given by a matrix U, a matrix sigma, which contains the singular values, and a transpose matrix V. Now, we've assumed that x does not necessarily have the same number of rows as the same number of columns. So in our case now, this matrix U is going to be a matrix of dimensionality n times n. This matrix sigma is going to have dimensionality of n times p, and this matrix V of t has dimensionality p times p. And we have the property that U transpose times U is equal to U transpose, and that's equal to 1. And the same with V transpose of V equal V times V transpose. Next thing we need now are also some further definitions. So we can think of U in terms of the vectors. So we would have a U0, a U1, up to UN minus 1. So these are the so-called left singular vectors. The matrix V is something we can now think of in terms of the right singular vectors, V1, V2, up to V of P. And these are the right singular vectors. The next thing we have is that these, or this matrix sigma is given now in terms of the singular values, sigma 0, sigma 1, up to sigma p minus 1, and the rest of them are 0. So what we have then is that these singular values are ordered so that sigma 0 is larger than sigma 1, larger than sigma 2, up to sigma p minus 1, larger than 0. The remaining ones are 0. What you will also see now, so let's run some calculations here. So if you take an example with a sigma given by 2, 0, 0, 1, 0, 0, this is an example of a matrix which could arise from a singular value decomposition. We can rewrite this in terms of a sigma tilde 0. And where now this sigma tilde has a dimensionality of 2 by 2. So let's see that. So if you can quickly see if we take the calculation of sigma t times sigma, that this becomes a 2 by 2 matrix in this specific case. And you will see that this becomes equal to 4, 0, 0, and 1. And that is the matrix which we get by performing that calculation. Similarly, in general terms, sigma t sigma is going to be a matrix which now contains only the non-zero values, only non-zero values. So let me just quickly see here, because there's a question in the chat here. So this is by definition in the singular value decomposition, so the sigmas can never be negative. And that is something which follows from the theorem when you perform the singular value decomposition. So they are never negative. And that's also another important property which we are going to use when we want to show that the matrix X transpose times X is going to be a so-called positive definite matrix. So we're coming back to that. There are several interesting links here with the singular value decomposition and the way we can analyze the standard ordinary least squares and ridge regression. When we have lasso regression, we don't have an analytical answer. And then it's more difficult to show this kind of mathematical connections which we are doing with ridge and lasso regression. No, ridge and ordinary least squares. So this is going to then be a matrix of dimensionality P times P. On the other hand, you will quickly see now if you take sigma times the transpose of sigma, this is going to be a matrix which has a dimensionality n times n. So if you look at the example which we have here, which is a 3×2 matrix, so n is equal to 3. If I take sigma times sigma transpose, it's going to be a 3×3 matrix, and you can easily convince yourself by that. And you will find that it has elements 4 and 2, and then it has rest of the elements are equal to 0. And then for the other one, when I take sigma transpose times sigma, that's going to give me a 2×2 matrix in this case. Now let's now look at X transpose multiplied with X, because this is a quantity which we have in ordinary least squares. So we can now rewrite that one in terms of V. So I'm just setting in the expression for the singular value decomposition, sigma transposed times U transpose times U times sigma times V of t. So this is just me plugging in the singular value decomposition. Now what I know here is that this now is equal to the identity matrix by definition. So this becomes simply V times sigma t times sigma times V of t. And this is a matrix, when we look at it, it is a matrix of dimensionality P times P. So this is important to keep in mind when we are performing these calculations here. Now, when we now look at the ordinary least squares, then we know that if I plug this in, what I have is that y tilde is equal to x times beta. And now we should put an OLS here and OLS. So let's now plug in the value for beta ordinary least squares. So this is the same as x multiplied with x of t, x transpose, multiply with x of t, multiply with y. So I am now using the singular value decomposition. So this becomes u times sigma v of t. And then I have v sigma t times v of t inverse of v of sigma t of u of t times y. Now there is a useful property now. So keep in mind also that the matrices which we have, V and sigma, they are now square matrices. So there is a small statement from linear algebra. So if we have two matrices, if A and B are square matrices, and both of these matrices, so we're also assuming they are square matrices and invertible, and A and B are invertible, then what we have is that A times B inverse is actually given by B minus 1 times A minus 1 here. Now, the thing with the matrices which we have, if we now look at the matrices here, this is a matrix which is invertible, and you can see that when you go back to the definition here. So we have a sigma transpose times sigma. This gives us always something in terms of the singular values which are non-zero. So that means that this quantity is always invertible. So you can now think of this as a quantity which is always invertible. And then the matrix V is an invertible matrix. It has an orthogonal, it's an orthogonal matrix, and the same applies to this one. So in this case, we actually have three matrices. So we could actually rewrite this as V inverse of T and multiplied with this matrix here, which we have to take as an inverse. So you could think of this as a matrix A and this as a matrix B now. And then simply invert them. And what we get then is that this matrix here is going to take away that one. This matrix here will take out this one. And this matrix here takes out this one times that one. But then what we have to be a little bit careful with now is actually that what we end up with. So we end up with the following. So it means that this y ordinary least squares tilde. So this is what the model gives us. It gives us now u of sigma, and then I have v of t times v, and then I have a sigma of t, sigma minus 1 times v of t times v, and then I have sigma t, and then u of t times y. But I have to be a little bit careful now because this, when I do the calculations now, is going to give me u times u of t of y. However, due to the fact that the dimensionalities of the matrices which you see here, these matrices here have dimensionality p times p, then what happens when I perform the calculations is that this is going to be given not by an identity matrix, but by a sum over I equals 0 up to p minus 1. So it's not the complete projection here. So I would have a u of I of u of I t multiplied with the vector y. So in a sense, what I've done now is that due to the fact that I have this singular value decomposition, I can now show that my ordinary least squares model, the y tilde ordinary least squares, is given by a projection of the original vector y by the orthogonal vectors of the matrix U, but I would not have all the orthogonal vectors. I have only the vectors which correspond to the singular values which are non-zero. Now, this has another very interesting property, and we are going to see the importance of that pretty soon here. So if we now look at this matrix X transpose times X, what this one is, it's equal to V times sigma T times sigma times V of T. So what I could do now is to multiply with the matrix V from the left, from the right. So that means that I have V of sigma T of sigma V of T times V, which is equal to the identity matrix. So this becomes simply equal to V of sigma T of sigma. And that means if we now think of the specific eigenvectors which I have, or the vectors of the matrix V, so V contains now the vectors V0, V1, up to V of P minus 1. So what I see now is that the vectors V of I are the eigenvectors. If you look at the equation which we have here, this one, if I take each component of V of I here, then these are the eigenvectors. Now the eigenvectors of the matrix X of T of X with the eigenvalues equal to sigma 0, sigma 1, up to sigma p minus 1. So the singular values are the eigenvalues of this matrix, which we have here. Now, this is an important result when we are looking at this analysis, because if you remember that the second derivative of the cost function, the second derivative of d beta t was equal to 2 over n, so this is something we showed last week, of x transpose times x. This means that since these singular values, since sigma 0 larger than sigma 1 up to larger than sigma of p minus 1 larger than 0, then that means that this matrix, which we call the Hessian matrix, that H is positive definite. And has a global minimum. So that's a very important property. Now, there's another property which we are going to show a little bit later, and that is that this matrix actually is given, this matrix which you see here, the Hessian, for ordinary least squares, gives us what's called a correlation matrix, and which is again based on a covariance matrix. Actually, this matrix here is directly proportional with a covariance matrix. But we are going to see that a little bit later. Now, what I want to do now is to go back to ridge regression. So if I perform the same analysis with the ridge regression, what I'm going to get then is the following. So I will get the beta ridge, which we have found equal to x transpose of x plus lambda times I inverse multiplied with xt times y. If I do the singular value decomposition, then I will find that this y of ridge is given by x, the design matrix, multiplied with beta ridge. And when I now perform the singular value analysis, what I'm going to get is that this is going to be given by a sum from j equals 0, and this is something I invite you to check, of u of j transpose multiplied with sigma j divided by sigma j squared plus lambda. So if I now compare this with the ordinary least squares, what you see now is that this is actually different. And the difference here now is going to be important when it comes to specific values of these vectors. Because what lambda is now going to do when we make lambda larger and larger, so we make it, let's say, 10 to the 10th, what that is going to do now is that is going to affect significantly the small singular values. So in ordinary least squares, we have this result multiplied. So this is then multiplied with y and y. So these are projections of the original data set. So you can think of ridge and OLS, the models which we get, as specific projections in terms of the singular value decomposition of a matrix and the singular, the left singular vectors and the singular values. Now, if we take a very simple case here, which illustrates everything which we have here, suppose now that we simply set the design matrix. In our specific case, we simply set the design matrix equal to a diagonal matrix. Suppose we do that. So let's suppose now that x transpose times x is equal to the identity matrix. So that's a very simple example which we can use. Now, if we do that, what we will see then when we put that one equal to that matrix is that we are going to get just 1 or 1 over 1 plus lambda. So that means that beta ridge is then simply, when we now look back at the expression here, is going to be equal to 1 over I plus lambda times I. Sorry. Let me just bring it up again. So I have I of 1 plus lambda multiplied with xt times y. That's the original result which we have. Now, for beta ordinary least squares, this is obviously just the inverse of the identity matrix multiplied with xt or y. So that's simply xt times y. And this is simply 1 over 1 plus lambda of xt times y. Now, what you see now is that this parameter lambda is going to drive the specific contributions from the parameters we've been fitting. It can drive some of them to 0. So let's look a little bit closer at the expression which we have here. So this simply tells us that lambda is driving this component, depending on the size of lambda, it's driving it to be smaller and smaller. If you now look at what we have here, if this sigma j is small and lambda is large, this means that lambda is going to quench contributions which have a small singular value. So next week, we are going to see that these small singular values, they are actually proportional to the variance of the ordinary least square calculations. And this means that when we now increase lambda here, since lambda is also larger than 0, and we have small parameters, it's actually going to drive some of the small parameters to become insignificant. And this is a way to reduce the effective degrees of freedom. So by tuning lambda, what we are actually doing now is that some of the parameters we are fitting, some of the parameters beta, they're going to be tuned away. And next week, we are going to see an explicit example of what this actually means. And then we are going to look at numerical calculations where you will see that increasing lambda is now going to drive some of the parameters beta to become less and less significant. So the impact of lambda is going to be larger on the smallest values. And we can, in that specific way, we can actually view lambda as a parameter which reduces the importance of some of the estimators or parameters beta which we are fitting. So next week, I'm going to pick up this thread again, and we are going to look a little bit more at the mathematics of ridge and ordinary squares. We're going to look at specific examples. You will find these specific examples if you take a look now into the slides. So I'm going to give that as a kind of small homework to you before we stop here. So if you go back and look at the Jupyter notebooks for the both this week, this day 1, which we had, and you can actually find that one by scrolling up here. So if you take a view on the Jupyter notebooks for the first and the second session, and then also do the same with the session which we have today, which is this specific session 3 here, where we have an interpretation of lasso and ridge regression. If you take a look at those as well, we will actually pick up this topic here next week as well. And we're going to look in more detail at the meaning of ridge and also lasso regression through some simple examples so that we can gain some understanding of what happens when we increase or decrease lambda. But you can see from the expression which we derived that when we increase lambda, if we have singular values which are small, then lambda is going to dampen the effect of these in our model. That is the main message. So these hyperparameters are also called shrinkage parameters because they can shrink the role of some of the fitting parameters which we are setting up. Okay, I don't know if this was clear enough, but I'm going to pick it up again next Monday, and we are going to look a little bit closer at that and also at the statistical interpretation. And when we're done with that, we are going to jump into so-called resampling techniques, as you can see from the plan here. So we are going to finish the region lasso regression, and then we're going to dive into resampling techniques and the bias variance trade-off. So I hope it was not too confusing. Take a look at the lecture notes here, and also at the basic notes which we have on for the Jupyter book, because that contains a more complete discussion of these topics. I'm going to stop here now. Stop